this video, we're going to talk about why e to the power of pi times I equals -1. Probably the coolest thing about this formula is that you don't actually need any technology or anything to discover it. In fact, if you were a caveman living before any mathematics was discovered, you could completely discover this on your own. But it did take a long time to discover it. How does it work? Possibly the first mathematical thing you've ever thought about, or was ever thought about, is addition. Addition is a pretty basic idea. Imagine you are one of the first mathematicians, probably a caveman, and you have 2 bananas, and then someone brings 3 more. This is all there is to addition. You just put these together, and you have 5 bananas. A step up from addition is multiplication. Now imagine that you have 2 bananas, and you can collect them every day, and you do this for 3 days. And if you get 2 bananas every day, this is just 2 plus 2 plus 2, 3 times. Notice that if you had to do this for 20 days, you would have to write 2 plus 2 plus 2 plus 2 plus 2, and this would be a lot of repetition. And it turns out that when you have repetition like this, oftentimes you can simplify it just with a notation. In this case, we invent multiplication and just write 3 times 2. In this case, this means that take 2 and add it to itself 3 times. The cool fact about multiplication is that it doesn't matter the order that you do it. So if you take 2 to be the amount of bananas and 3 to be the number of days you collect them, then it turns out that this is the same as 3 plus 3, or collecting 3 bananas for 2 days. The next idea is powers. This idea works so well that you can repeat addition and call it multiplication. So you might ask, what if you repeat multiplication? 2 times 2 times 2. We invent the idea 2 to the power of 3. Where would this come in real life? Well, imagine you have a bacteria, and every day it divides into 2. And then each of those divide into 2. And same with those ones. As you can see, pretty soon you have a lot of bacteria, but in fact, all you do here is multiply by 2 each time. This is a property of exponentials. They can get pretty big pretty fast. We just started off with 2 fairly small numbers, 2 and 3, and we already have 8 bacteria on the 3rd generation. Also, you might wonder, does these switch? But it turns out this is not commutative, so this is not the same as 3 times itself, 2 times. The next idea is inverses. The idea of an inverse is basically just taking the opposite of all those operations. So if you have 5 bananas, then the opposite of adding 3 is taking away 3. And this is really all there is to subtraction. But the thing to remember is that subtraction is really the opposite of addition. Then there's division. Division is just the opposite of multiplication. This is pretty basic too. If we want to take the inverse of a power, there's two choices. If you have something like 2 to the power of 3 equals 8, then for the inverse you could either ask for the base 2 or for the power 3. If you say 2 to the power of what equals 8, then this is a logarithm. And we call this log base 2 of 8, which is just saying, what do I have to take 2 to the power of to get 8? If you want to ask for the base, then you say 3 rid of 8. And this is just saying, what do I have to multiply by itself 3 times to get 8? It turns out that a very special base is e. So e to the 5 is e times e times e times e times e. But e is a special rational number, approximately 2.71, and it's so special that we also like to take the logarithm base e a lot, and we have a special name for this. We just call it natural log, ln. The next question with powers is what's 2 to the power of, say, 3.1? Well, this is 2 times itself 3.1 times. So 2 times 2 times 2 times 0.1 of a 2? That doesn't really make sense. It doesn't make sense to multiply something by itself 3.1 times. It turns out that our original definition is repeated multiplication doesn't work if we have a number like 3.1. It only works for what are called the natural numbers, like 1, 2, and 3. In order to find out what a power is for anything that's not a natural number, we're going to have to extend the definition of a power, and this will lead us on the way to finding how to take e to the power of something like I. The next idea is variables. A variable is basically just a box that can hold a number in it. If you have an equation like x plus 2 equals 5, then you know that you can just find the value of x. A bigger idea is functions. This is something where we consider every value that the variable can have. And then we do something to it, and we get our function, and we consider every value that can have. For example, f of x equals x plus 3. Based on the operations we've talked about so far, we can have functions that involve addition, subtraction, multiplication, division, and powers. It turns out any function involving multiplication, addition, and subtraction will be a polynomial. And polynomials always look like this. Where you have a bunch of things added together that are all power functions. The graph of a polynomial can pretty much look like anything in the middle, but it always goes off to positive infinity or negative infinity on the left and right sides. The next function is a power function, which is just a variable raised to some power. Power functions either look like this or like this. And they can be flipped because you can have a multiplier out here. In a sense, the opposite of a power function, instead of a variable to the power of a constant to the power of a variable, looks like this. Note that in order to talk about this graph, we still have to figure out what it means to take a variable or a number to some things like the power of 3.1. And so far we only know how to take them to the natural numbers 1, 2, 3. But once you learn that, it'll look like this. One side will go off to positive infinity and one side will get closer and closer to 0, which makes sense if you think about bacteria or mold. There's just a little bit of it and then all of a sudden there's a ton of it. Remember, one of our favorite exponentials is e to the x. The last two functions we're going to have to talk about are sine and cosine, but we haven't introduced these yet. The next variable we have to, or the next part of the puzzle we have to talk about is pi. If you have a circle, then if you take the diameter, you could measure, or the circumference, you could measure this with, say, a string, and the diameter, you could just easily measure this with a ruler, and you take circumference divided by diameter, this will always be the same number, pi, approximately 3.14. It's irrational, but once you found enough digits that you want and calculated at once, then if you know the diameter, you can always get the circumference and vice versa. The next important thing in geometry is trigonometry, or triangles. Trigonometry starts out with triangles, specifically right triangles. If you have a right triangle, then you can look at some angle that isn't the right angle, and it'll have an opposite side, an adjacent side, and a hypotenuse. And then you have the SOHCAHTOA. One of the cool things about this is that no matter what size the triangle is, as long as it has a right angle and this angle, these ratios will always be the same. And that's why we can uniquely talk about the sine or the cosine as being the value of these ratios. The next idea is, what if you want to take, so if you want to take the sine of, say, 30 degrees, well, you could find a 30-degree triangle, calculate the ratio, and once you've done that once, just like with the circle, it'll always be the same. And now if you know the adjacent, you could find, say, the hypotenuse, or the opposite, you could find, say, the hypotenuse. What about the sine of 270 degrees? Well, if you try to draw a triangle with 207-degree angle, you can't do that. In fact, this definition really only works if the angle is between 90 degrees and 0 degrees. Just like with the exponentials, where it doesn't make sense to take 2 to the power of 3.1, so far it doesn't make sense to take the sine of anything larger than 90. But we can extend this definition just like we're going to do with the powers. The idea is to take a circle called the unit circle and put a triangle in it. This circle has the radius 1, so the hypotenuse is equal to 1. Here, we mark the point where the line from the origin crosses the circle. And this case, since the hypotenuse is just 1, the opposite, or the sine, is just this opposite, which is the y-coordinate, and the cosine is the x-coordinate. It turns out we can define the sine and the cosine to just be these x and y coordinates. And now, even though you can no longer draw a 270 degree triangle, if we want to know what the sine of 270 degrees is, that's just the point where this line crosses the circle. If you want to know the sine of 91 degrees, it's this point. Even negative angles, we can now calculate it. If you look at what the sine does, is this angle increases, the x and the y both go up and down and up and down, so their graphs look like this. This is f of x equals cosine. We now write cosine of x because we're thinking it just of as a function, not of some angle. And this is what this sine graph looks like. The next idea, degrees are really nice and easy to understand, but in mathematics, we need to use radians, in which is just a unit where instead of a full circle being 360 degrees, it's equal to 2 pi radians. The next idea is differential calculus. If you've taken differential calculus, you should be able to follow this pretty easily. If you haven't, it'll be a fair amount more confusing, but hopefully you should still be able to see the big ideas and enjoy those, even if you haven't heard of what a derivative is before. The basic idea of a derivative, say you're driving a car, and you know how far you went and how long it took, then it's easy to find your speed. Your speed is distance divided by time. This is a really nice formula, but it only works if you're going the same speed all the way. If your speed was changing, then this formula would no longer work. So we could ask, it doesn't make sense anymore to talk about what your speed was for an hour if some of the time you were going 60, some of the time you were going 40, some of the time you were going 90. But it does make sense to talk about your speed at an instant. That's what your speedometer reads. The idea of a derivative is that we want to know what your speed is at every instant. One of the special things about a derivative is that oftentimes we'll have a function, some function of time in this case, that is equal to the distance, and the derivative will transform it into a function of speed, or a function of time, that gives us the speed. On a graph, if this is the original distance graph, then the derivative will look like the slope of the tangent line at every point on this graph. The idea behind this is, how do you find the slope of the tangent line? Well, if it was constant, you could just take the change in y divided by the change in x. And this would be the slope, but it's not constant. The idea is that if this is pretty small, then this is going to be close to the actual change in y. So you could just take the function at some further point take that change in y and divide it by the change in x. And then if you bring these really close together in the limit, you can get the slope at that point. The other important idea about the derivative is that the derivative is what's called an operator, which is basically a function of a function. So it takes some function and turns it into another function, unlike functions that we're used to, which turn numbers into other numbers. A nice example, f of x equals x squared. The derivative turns this into f of x equals 2x. For this video, we're going to need the derivatives of powers, the derivatives of exponentials, the derivatives of sums, the derivatives of sine and cosine, and the derivative of a plain number multiplying another function. So these are all the corresponding derivative rules. This is the power rule, this is the exponent rule, sum rule, and so on. Here you can see that the derivative of an exponential is just the exponential times a constant of proportionality, and that constant is the natural log of a. Remember that the natural log was just the log base e, which explains why e is so important, and especially the logarithm base e. In fact, this is really why it was so special that we gave it its own name. A special exponential to consider for this is when the base is equal to e, then f of x equals e to the x, f prime of x equals e to the x times ln of e. But remember, ln of e is logarithm base e of e, so we're asking, what do I have to take e to the power of to get e? And the answer is 1, therefore the logarithm base e of e is 1, and we see that this is just a multiplier of 1, so the derivative of e to the x is just itself. Here, the derivatives of sine and cosine are just negative sine and cosine, so you see that if you keep taking derivatives, these will repeat. In fact, if you keep taking derivatives of e to the x, that'll repeat too, which turns out to be pretty important. In fact, we'll write down the e to the x rule as its own rule. Oops, this is supposed to be x. Also, this only works when sine and cosine are in radians, which explains why we have to use radians even though they're not as nice as degrees. The next idea is imaginary numbers. Unlike the name, imaginary numbers aren't like a fantasy. They are real numbers. This is just what they're called. The idea behind imaginary numbers is, remember, if you have something like x squared equals 25, then you can solve this by using a root, since the roots are the inverse of the power. In this case, we would say that x equals the square root of 25, which is equal to 5. But remember that there's another number which satisfies this, namely x equals -5 also works. So we say plus or minus 25, square root of 25. In this case, you can see that the square, if we take x squared equal to a positive number, then we're going to get a positive and a negative number. What about x squared equals -25? Well, there doesn't seem to be anything that works here, since every positive number squared and negative number squared is always positive. So, what do? It turns out we actually invent another imaginary number whose square is positive, or is negative. If you take x squared is equal to -1, then we just say that x is equal to the square root of -1, and we call that a new number called I. Also, note that if you reverse this, since the inverse of the square root is a square, you see I squared equals -1. Also, note that if you take -I and square it, this is also -1, so really the solution to this equation was plus or minus I. All the numbers that we were used to, like 5 and -7 and 1/2 and pi, are called real numbers. And in the context of imaginary numbers, we call these pure real numbers. If you take any of these things and multiply it by I, these are called pure imaginary numbers. The next idea is that if you add to these, say 2 plus 3i, we call this a complex number. Turns out once you have the complex numbers, even though we could take, say, the square root of -1, and we didn't know what that is, there aren't really any more surprises. Adding, multiplying, even taking the powers of complex numbers will just be another complex number. The only real surprise still left is dividing by 0. And it turns out that we can add these complex numbers just by adding each of these parts and almost treating I like a variable. And remembering that its square is -1, we can multiply it out the same way you learn to multiply sums in algebra, and we can even do something like 2 to the power of I, although we haven't learned that yet. Also, we have something called the complex plane, where you just treat the real part like an x-coordinate and the imaginary part like a y-coordinate and put it on the graph. And we say that this is what the number looks like in the complex plane. The last important idea is what happens when you take powers of imaginary numbers. Well, you can start out with I to the 0. We haven't proven this, but an important thing you need to know is that anything to the power of 0 is equal to 1, except 0 itself. 0 to the power of 0 is undefined. So, even I, as strange as I is, to the power of 0 is 1. I to the power of 1 is I, because anything to the power of 1 is itself. I squared is equal to -1. We already said that. I cubed is equal to I times I squared. Using exponential addition, this just uses the idea that 2 i's times 1 I is 3 i's, which is I times -1, or -I. I cubed is I squared times I squared, which is -1, which is just 1. Oops. And I to the 5th is I to the 4th times I, which is just I. And you can see that this will repeat forever. The next idea is infinite series. One of the cool surprises in mathematics is that you can add an infinite amount of things and still get a finite result. So for example, you could eat a piece of cake for eternity and still not end up eating an infinite amount of cake in the end. How is this possible? Well, say that you have a pie and you only have one pie, but you accidentally invited an infinite amount of guests to your party. And the question is, how do you feed them all? Well, what if you find out that it turns out it doesn't matter to the guests how small of a piece of pie they get, they just want to try it, even if their piece is really, really small. It turns out you can feed all the guests. How? Give half the pie to the first guest. Give half of that to the second guest. Give an eighth of the pie to the third guest. Give a 16th to the fourth guest, and so on. And then you can see that you fed all the guests. Now say that the next time the party comes, all the guests bring their own piece of pie that was what they got last time, and they all put it together. Well, then you have a half of a pie, plus a fourth, plus an eighth, plus a 16th. And you know that this is just equal to 1 since that was the original. In this case, this is sort of a surprising fact. We add an infinite amount of things and still get a finite number. The next thing you might wonder is this because these terms decrease? Remember that it's better to get half a pie than a quarter of a pie. All these terms are smaller. If the terms always get smaller, will it always be equal to something finite like 1 or 5 or 7? Well, if you have this series, it turns out that even though these terms get smaller, this series is equal to infinity. So there's something fundamentally different about these two series. Even though this series gets smaller, and this series also gets smaller, this series has a finite sum, and this series has an infinite sum. You might ask, how do you tell the difference between series like this that add up to a number like 1 and series like this that add up to infinity? And it turns out there really is no way to tell the difference directly. You have to look, and sometimes it can be hard to tell the difference between these two types of series. Series like this are called convergent, which just means they add up to something like 1. And series like this are called divergent, which either means that they add up to infinity or they don't add up to anything at all, like the series 1 minus 1 plus 1 minus 1, which just goes back and forth. The next idea is Taylor series. The idea of a Taylor series, remember we talked about a polynomial, and we said that aside from the fact that they always go off to positive and negative infinity, if you have enough terms, they can look like pretty much anything. Well, one question is, could you make them look like, say, an exponential, given enough terms? It won't be perfect, but you could. Or could you make them look like a trig function? And you might ask, if you have an infinite amount of terms, could you get this, like, say exact? And it turns out that you can. If you have an infinite amount of terms, you can turn a polynomial exactly into an exponential or a trig function. How do you do this? The idea is that you start off by writing f of x as a polynomial. F of x is some general function, any function, that we want to write as a polynomial. And this goes on to infinity, then all we have to do is find these coefficients, a0, a1, a2, a3. We could try and guess them, but that would be really difficult, and we'd never guess an infinite amount of them. So how do we find them? It turns out that there's a nice trick using derivatives. If we take the derivative of this series, recall that the derivative of a sum is the sum of these derivatives, and these coefficients really don't matter. This is a1. We just put the 1 in to help see a pattern. We're also going to write it this way to help see a pattern. We're actually just going to write these going the other way. The third derivative, we can write the third derivative just using this notation. And so on. And then the idea is that we plug 0 in. In this case, f of x is just a0 plus 0 plus 0, or just a0. Oops. Prime of 0 is just a1. So, the general one is this n times n minus 1 times n minus 2 times 3 times 2 times 1 an. What is this n minus 1 times n minus 2? It turns out that this turns up and it's so useful that we give it a name. We call this n factorial. And an n factorial is just every number less than 1 and n multiplied by itself. So for example, 3 factorial is just 3 times 2 times 1, 6. For this example, we could divide by n factorial, and we see an equals f of 0 for n factorial. So now we found these coefficients, and we know what to put in to approximate f of x. In this case, f of x equals Also, you should know that by definition, 0 factorial is 1, so this just helps go with the pattern, and the 0th derivative of f is just f itself. So, f of 0 plus and this is the Taylor expansion. This is how we generate a series for any of these things. Let's do 3 examples that are really important. And we're almost there to the final e to the pi I. So how do you do this? First, we usually just find what happens when you differentiate something over and over and over again, and then we just put it into this series. So f of x equals e to the x, f prime of x equals e to the x, f prime of x equals e to the x. It's pretty clear what's going to happen. We just differentiate it and nothing changes. It's always e to the x. What about at 0? Remember, we said anything to the power of 0 is 1, so this is just 1. In this case, if we put this in here, then we have e to the x equals 1 plus 1 over 1 factorial. And now, we're going to put this up here because we'll need it later, just simplifying a little bit. The next one is sine and cosine. If f of x equals sine, then we take a derivative. And over and over and over again. Just like e to the x, we see that this just repeats over. The repetition is a little bit more complicated, but we see once every 4 turns, we'll just get the same thing again. So if we plug in 0, you should know that the sine of 0 is 0 and the cosine of 0 is 1. You can see that from the unit circle. Oops. What did I do here? That's 0. So, if you plug this in, then sine of x equals 0 plus simplifying, so this is just the same thing as e to the x, but they're all odd and they go negative and positive. So we'll write this right underneath e to the x. Now cosine, which is a lot like sine, f of x equals cosine x. And you can see, just like before, it takes four iterations for this to repeat. So at 0, it's 1, 0, minus 1, 0, 1. What did I do here? So if we plug this in, cosine of x equals and so on. So simplifying, we're just going to write it up here. So you can see cosine is a lot like sine, they're just all even this time. So you can see that all of these are really similar. In fact, it almost looks like if you put these together, you just get e to the x. These are all the odd ones, these are all the even ones, and these are all of them. But you can see that the thing that gets in the way is these negative signs. So what do we do? Well, it turns out that it's also time to answer a different question. Namely, how did we take 2 to the power of 3.1? Well, it turns out that it's easier to first answer the question, what's e to the power of 3.1? It's not e times itself 3.1 times, but we could just plug 3.1 into this series, and now we know. Well, what about 2 to the power of 3.1? It turns out, we're not going to prove it, but we could use anything to the power of something else is equal to a to the b is equal to e to the b natural log a, and you still have to figure out how to find the natural log of a, but there's a Taylor series for that too. And if we plug it all in, we can find out what 2 to the power of 3.1 is. It turns out we can take e to the power of even stranger things. We can take e to the power of I, and that's what we're going to do. E to the power of ix. So we just plug ix in. This is using something called the product of the powers, which you can just kind of distribute this power. Now, remember, actually we're going to add a couple more terms. So, remember what those powers of I were? It turns out that these powers of I repeat, sort of just like these series, and that's very useful. Now we just group the real things and the imaginary things and factor out I. And this is a series for sine, and this is a series for cosine. And since these series are always true, even for imaginary numbers, this is just cosine x plus I sine x. So, we've got all our use for now out of Taylor series. We don't need them anymore. So, this really cool thing is called Euler's identity, or Euler's relation. Euler was some guy a long time ago that discovered this. Oops, not there quite yet. Now this is pretty cool. These exponentials that we talked about from repeated multiplication, e cubed is e times e times e, and these trigonometric functions that we talked about from triangles, SOHCAHTOA, it turns out that these are connected and are in a sense the same. E to the I exponentials can be written as trig functions, and trig functions can be written as exponentials, it turns out. So the very last thing to do is remember we do this in radians. So we could just plug pi in, and e to the pi I cosine of pi plus I sine of pi. Remember that pi is 180 degrees, so you can see from the unit circle, cosine of pi is equal to -1, and sine of pi is equal to 0. So we have e to the pi I equals -1. And that's how you figure it out, going all the way from addition to Euler's relation.